This lecture is brought to you by students from the Department of Chemical Engineering, University of the Philippines, Los Banos. Today's topic is gas absorption operation design. This report will tackle some introduction about the gas absorption operation, some basic concept about the equipment design, the two basic type of equipment which are the pack and the plate tower, other complex systems like multi-component and absorption with chemical reaction. The objective of this lecture are the following. This will help you understand the operation through the discussion of important concepts and solving some related problems.
Gas absorption. According to McCabe, soluble vapor is absorbed from its mixture with an inert gas by means of a liquid in which the solute gas is more or less soluble. It involves molecular and turbulent diffusion or mass transfer of solute through a stagnant non-diffusing gas B into a stagnant liquid C. In simpler terms, we define gas absorption as a unit operation in which soluble components of a gas mixture are dissolved in a liquid according to Perry. We find applications of the said operation in nitric acid manufacturing, in which absorption of nitrous gases in water or nitric acid is done. In the hydrogenation of edible oils, H2O gas is bubbled into oil and absorbed. Gas absorption is also used to control air pollution. Flue gas and other gas pollutants are absorbed by contacting it with liquid. Removal of CO2 from water gas also uses gas absorption. In designing, we have to consider the following. First, the plates or packed elements, which are the usual venue of gas absorption. Second, the countercurrent flow, which gives us better mass transfer between the fluids. Also, we have to take note of the data on gas liquid or vapor liquid of the system at hand, information on the liquid and gas handling capacity of the contacting device chosen for the particular operation, and determination of the required height in contacting zone for the separation to be made as a function of the properties of the fluid mixture and mass transfer efficiency of the contacting device.
Factors that must be determined in a system design are the solvent, gas velocity, height of the vessel, optimum solvent circulation, temperature of the streams, and the pressure. For the best solvent, it should have high solubility. It should also be non-volatile, inexpensive, non-corrosive, not viscous, non-foaming, and non-flammable. For most gases, we use water. For light hydrocarbons, oil is used as best solvent. The important quantities in system design are gas flow rate, gas composition, operating pressure, degree of recovery of solutes, and solvents to be employed. For the tower height, it depends on phase equilibria, degree of removal of solute from gas, and mass transfer efficiency of apparatus. Solubility data comes in three forms. It can be expressed as solubility in weight or mole percent, also known as Henry's law coefficient. It is also expressed as pure vapor component pressures or equilibrium distribution coefficients or K values.
The next topic that we will discuss is pack towers and its design. When will pack towers be used? First, it is good in handling corrosive materials. It is also good for liquids that produce foams due to its structure that prevents foam formation. And lastly, it is used to attain conditions that requires a very low pressure drop. Pack columns are used for contaminant management, especially in removing volatile components. For setups where the boiling points of components are near to each other, pack columns can also be used. The tabulated composition of contaminants is required in order to plot equilibrium line. This line will be used in designing the tower and stage number determination. In cases that the tabulated data is unavailable and the concentration of contaminant is very small, we can use the Réault's law to estimate the curve under this application. The simplified balance equation shown below can be used in the construction of the operating line. This line, along with the equilibrium line, will be used in the graphical analysis of tower parameters.
And to further understand the design parameters for back tower, here is a quick example. Suppose you wish to remove acetone from a gas stream of 10,000 moles per hour in a back column. The inlet gas contains 2.6 mole percent acetone and the outlet gas stream can contain no more than 0.5 mole percent acetone. Assume a pure water stream enters the back tower at a rate of 8,000 moles per hour. How much acetone will be there in the outlet liquid stream? Given the diagram, we will let L in and L out be the molar flow rates of the inlet and outlet liquid stream respectively. G in and G out be the molar flow rates of the inlet and outlet gas stream respectively. X in and X out be the mole percent of acetone in the inlet and outlet liquid stream, and Y in and Y out be the mole percent acetone in the inlet and outlet gas stream. As specified in the problem, L in equals 8,000 moles per hour, L out equals 8,000 moles per hour, G in equals 10,000 moles per hour, G out equals 10,000 moles per hour. X in equals 0, Y in equals 2.8 mole percent, Y out equals 0.05 mole percent. The missing information for this problem is X out. Using component balance, we have L out X out plus G out Y out equals L in X in plus G in Y in. Substituting the given values, we get 8,000 X out plus 10,000 times 0.005 equals 8,000 times 0 plus 10,000 times 0.26. We can now solve for X out. Isolating X out from the equation, we obtain X out equals 0.02625, or the liquid stream can contain 2.625 mole percent acetone. For back towers, we should be reminded that the equilibrium and operating lines are constructed as follows. Just as in the McCabe-Tilly analysis of distillation, the equilibrium stages are stepped up between the two lines. Note that for stripping, the operating line would be on the other side of the equilibrium line. Once the theoretical number of stages have been determined, we can proceed with the design of the column by following 3 steps. Step 1, selecting the type and size packing. Step 2, determine the column diameter. And Step 3, determine the column height. Here is a guide problem for us to have a good grasp of the previous concept. Specify the packing type and column dimensions for a column that will be used to remove chlorine from a gas stream using an organic solvent. Assume the separation requires 20 theoretical stages. The vapor flow is 7,000 kg per hour. The average vapor density is 4.8 kg per meter cube. The liquid flow is 5,000 kg per hour. The average liquid density is 833 kg per meter cube. The liquid's kinematic viscosity is 0.48 centistokes or 4.8 times 10 raised to negative 7 meters squared per second. We will answer this problem following the 3 steps given earlier. First, we must select the size and type of packing. There are 2 types of packing. The random packing, which comes in a sack and is simply dumped into the column, and the structured packing, which may come in bales or intricate designs that are stacked in specific patterns. There are readily available tabulated design values for packing factors, such as packing type, material, and nominal size. Here is an example of such. These values were taken from the available designs in the industry. The nominal sizes given can either be in inches or in millimeter. Generally, the column diameter to packing size ratio should be greater than 30 for Rashig rings, 15 for ceramic saddles, and 10 for rings or plastic saddles. Moreover, the geometry of our packing will typically be a function of the needed surface area and or allowable pressure drop. If several packing meet your requirements, you should choose the least expensive as long as it has an acceptable operating life. For example, you will choose plastic ball rings over the metal ones because plastic is cheaper. Note that for columns over 24 inches in diameter, number 2 or 2-inch packing should be examined first. Most methods for determining the size of randomly packed towers are derived from the Sherwood correlation. A design gas rate, G, can be determined with the help of the following figure, which is based on the correlation from the Sherwood equation. This is a design gas rate chart. This chart is used for determining the flooding and pressure drop in random packed towers. These guidelines are designed around flooding pressure drops documented in literature. In other words, for most cases, designing with these pressure drops should help you avoid flooding. Going back to the problem, since we are designing an absorber, we will design for 42 mm water per meter packing. Actually, you could design for a lower pressure drop, but the column will increase in diameter and cost. In reading the design gas rate chart, you should first evaluate the x-axis. The x-axis value of the chart is equal to liquid mass flow rate divided by the gas mass flow rate multiplied by the gas density divided by the liquid density raised to 1/2. Substituting 5,000 and 7,000 kg per hour for the liquid and gas mass flow rates, 4.2 kg per meter cube for the gas density, and 832 kg per meter cube for the liquid density, we get 0.0507 as our value for the x-axis. You might be wondering why 4.2 kg per meter cube was used for the vapor density, since the given average vapor density was 4.8 kg per meter cube. However, you should be aware that at the top of the column, the vapor will be less dense at its highest velocity. This is what you should design for. As a rule of thumb, reduce the average vapor density by about 15% for the design. However, if you can get the real data from a similar tower, certainly do so. Since we already obtained the value for the x-axis, we can now plot it in the design gas rate chart. First, locate 0.0507 in the x-axis. Extend the point vertically until the line intersects with the 42 mm water per meter packing line. Reading the intersection of the 42 mm water per meter packing line and 0.05 on the axis, we find the value of 1.5 for the y-axis. From the previous chart, we read a packing factor of 24 for 2-inch plastic ball rings. All other information is known, so we can solve for G as shown on the y-axis.